was with all those answers, I went through and tried to highlight in green the things that would be potentially problematic. For sure, the one that I had to look up was the nitrile. The nitrile runs once, just as a single nucleophilic attack. Why would it hold up once and not continue on twice? Remember that hydrogen came from the acid? That's where we'd end the single addition. Okay, we still have a polar pi bond, but that nitrogen with that negative charge is going to make it very difficult to have another nucleophilic attack. Okay, so that's what limits that reactivity, which is why it really only does it once. We stop at the negative nitrogen, we then protonate with step 2, and we have our answer. There was a question about why we use methanol. Okay. The reason we use methanol in this case, because if we use H3O plus, we're also adding H2O. H2O is a nucleophile that will react with that functional group. Okay. When are we going to discover that? Chapter 18. Okay. So until we've covered that, we're trying to neutralize that effect or avoid that topic, and that's why we're saying the methanol there is our proton source. The lower right-hand corner, we might predict it to go out to NH2. It goes all the way out to NH3 plus and not NH2, and that's because of the reactivity of our nitrogen. Our nitrogen is a decent base. Under acidic conditions, it's going to protonate. You should be seeing that hydrogen on there, and it should be positively charged. That is a tricky one when it comes to smart work, because sometimes the online program is good about that and actually protonates it. Sometimes it's not so good about that. Okay? So if you end with a nitrogen in acidic conditions, protonate it first. If it's saying you're wrong, deprotonate it, try it then. Okay? And then you can send me an email complaint. Because you've now troubleshot what the problem was, you can send me an email complaint and I'll try and get them to fix it. If it's still saying you're wrong, you're probably missing something else. You should be sending me an email anyway to be like, why am I getting it wrong? Make sense? Okay. So we will see that nitrogen come back and be bothersome again. The very top one is straightforward. The one immediately underneath it, you notice the answers that we're getting, I'm being kind of lazy there, I apologize, is our starting material and methane. Okay? In a short answer, you should probably show both structures. In a multiple choice, you'll see probably one or the other. Okay? More than actually both are possibilities. Okay? What you would have to be careful of is to make sure that you don't just, it's a Grignard, so I react carbonyls. We have to watch out for acidic hydrogens. Okay? Back in semester 1, I did tell students that had me that you should memorize some pKa's because they can become problematic and it's useful to have that knowledge. Okay? So those of you that have not had me, I'll tell you that too. You should memorize pKa's for the common functional groups, okay? Because it can really help predict some of their reactivity. It is not a requirement, but it can simplify your life, okay, if you do so. If you had bothered to memorize the pKa of that phenol is about 10. That's pretty acidic. That's more acidic than water, and Grignards react with water. Okay? And then the last one, most students get stumped by seeing CO2, but if you draw out the Lewis structure, what becomes apparent? The polar pi bonds, the carbonyl, it reacts just the same. Okay? You notice that we don't end in an alcohol, we end in a carboxylic acid because there were 2 carbonyls, and we can only react 1. Okay? Questions about what's up there? I should have asked that first instead of talking through each one. You good? Okay. Cardy's done a pretty decent job drawing attention to some Grignard reagents or possibilities. Right? In the lab, we see the phenyl magnesium bromide right in the middle. Right? But it can really be virtually any alkyl halide. Right? So we've got a bunch of varieties of examples. Right? We're starting with an alkyl halide. We add magnesium. The magnesium inserts itself between the carbon and the halide. Does it have to be bromine? No. Bromine is just large enough to stabilize some of those radical intermediates to make it run a little bit smoother and faster. So it is typically shown with bromides, but it does not have to be bromide. Okay? We move to the bottom. He goes through and says, well, these are now not feasible. What do you see as the difference between the top ones and the bottom ones? What's that? Functional group. What do you mean?
Alcohol, carbon.
So getting really specific on it, right? The less specific might be in the top, we're highlighting red, right? Red to point out the reactive site for our Grignard. We look at the bottom, we're still pointing out that red, right? But in each of these cases, what else are they pointing out? A blue site. What is happening with that blue site? So let's take a look at the very first blue site. What functional group is that? An alcohol with a pKa approximate to water, meaning the Grignard would react with it. Okay? So the instant I form the Grignard, the molecule where the Grignard is would immediately react and pull that hydrogen off. What did that do to the Grignard? Killed its reactivity. Right? So that has an acidic hydrogen. The next one. Why is that next one problematic? There's not an acidic hydrogen there. Okay? Though I'm going to pause on that one. There is a hydrogen connected there. Okay? What functional group is this? It's an aldehyde. What you should be able to go through and do is prove, using all of what we've talked about, charge, size, electronegativity, all that, that hydrogen is not acidic. Okay? You should be able to prove that on your own. It is super common for students to try and remove that hydrogen. It is not acidic. Okay? So why is Cardy then highlighting that carbon if it's not an acidic hydrogen? So the red part is our nucleophile. The blue part could be what it attacks, an electrophile. Okay? If our Grignard has an electrophilic site or an acidic site within it, it's going to kill the Grignard. The whole point of making a Grignard is to react it with something. And typically that something is something else. Okay? If our attempted Grignard reagent has active sites within it, we're going to get a self-reacting structure, likely generating polymers, which is typically not what we're trying to do with a Grignard. Okay, we want a more controlled reaction. So that second one, that carbon is an electrophile. In the third one, what's Cardy highlighting? That one's trickier. Is that carbon electrophilic? To be electrophilic, it would need a leaving group. Is there a leaving group connected to that carbon? What's that? There are hydrogens connected. Would I ever expect the hydrogen to act as a leaving group and remove electrons from the carbon? No, because hydrogen can't stabilize that negative charge. Hydrogen is a lower electronegativity than carbon. Okay, so there's a lot of reasons that the hydrogen doesn't make sense. So there's no leaving group there, right, which means it's not acting as an electrophile. Why is Cardi highlighting it? It's not an electrophile, it's acting as. What's bad to have in your Grignard reagents? Secondary electrophiles and acidic hydrogens. Is that hydrogen acidic? Yeah? Why? Because the bromine's a good leaving group. We'd run an elimination reaction. Okay? So we do have acidic hydrogens here. Last one. Why is that carbon reactive? Does it have a leaving group?
Yes.
Right? Does that oxygen want to break away? Yes. Why? Say that again? Ring strain. We've got an epoxide. Epoxides want to break open. They just need a strong nucleophile to attack. Okay? The Grignard is a strong nucleophile. The Grignard could attack. We have an electrophilic site. Okay? So when we look at our Grignards, we need to be careful to ensure that there's only one place that I can generate a nucleophile. Okay? And I need to make sure there's no other electrophilic site within the molecule. Okay? Last question, kind of a review question. You'll notice that Cardi did not highlight the orange carbon of the epoxide. Why not? Why is that one not an electrophile in this case? Say that again?
Uncharged.
What do you mean by it's uncharged?
Nucleophiles attack because of state hindrance.
Okay. With our epoxides, there were two ways that we could get a ring opening. If we had our oxygen of our epoxide being neutral, it must be forced open with a strong nucleophile. What is the Grignard? A strong nucleophile, which then favors the least sterically hindered site of attack. Okay? So Lee and Alex together formed exactly what we're talking about, recognizing the chemistry within that. Could we possibly have made that orange site an electrophile with a Grignard? It's a harder question. To have a nucleophilic attack at the orange site, what must be true? It is sterically hindered. Kind of neither here nor there.
Do you need to change the conditions?
What do I need to change the conditions to?
Acidic.
They need to be acidic conditions so that the acid protonates the epoxide, making it be a good leaving group. Could I ever have a Grignard attack that orange position? No, why not?
Because you're under acidic conditions.
I'd be under acidic conditions, which would kill the Grignard. That orange site will never be a valid electrophile with a Grignard. Okay? Recognizing the conditions under which each of these reactions work is what allows you to predict and move forward. Yes, that's challenging, so good on you for nailing that down. Okay? We're not going to turn it into a quiz. But we will move into the next carbon nucleophile. We'll look at the wittig reagent. So here's our classic wittig system written up here. Okay, what appears to have happened in this reaction?
Elimination.
Okay, in elimination, what did you eliminate?
The bromine, and you formed a double bond.
Okay, we eliminated a bromine and we formed a double bond. So if I ran an elimination reaction with that, the bromine would leave, and then what would happen? I'd form a pi bond, right? I keep inverting that. And I'd have that, right? And I'd have an elimination reaction. Is that what happened? No. So I like that you're referencing an elimination, okay? The reason why I would say I like that you referenced an elimination is what did you end with? A pi bond. That's a really big tip that you did an elimination. However, what did you start with? You also started with a pi bond. Those of you saying the bromide doesn't have a pi bond are absolutely correct. But if you're going to make the argument that this is an elimination reaction, you need to make sure that the only thing that happened was that you eliminated a leaving group and a hydrogen. Is that the only thing that happened? Where did these carbons come from? We've somehow combined these two pieces through the course of this reaction. Okay? So this is not just a simple, straightforward elimination, addition, any of that. Okay? Another big tip-off that we could say that, Mike, that was a dumb question, you shouldn't have asked that, is how many steps are there? 3. So there's a bunch of different things going on to get that process to occur. Okay? So when looking at a reaction that you know nothing about, try to find patterns within it. Look at your reactants and products and see what things have changed. Okay? We can identify the red, we can identify the blue. Somehow those pieces were connected to each other. Okay? 1 and 2, that looks confusing. PPH3, how many times have we looked at the reactivity of phosphorus? Silence is a pretty appropriate answer. 0, we haven't talked about it. Right? That's going to be hard. We haven't talked about it. Butyl lithium. We talked about that reagent. Okay. Have we talked about carbonyls? Have we talked about alkyl halides? Yes. Okay, so let's take a look at those pieces and see if we can try and come up with a process that would have allowed this to happen. Okay? So if we look at the alkyl halide, we're likely taking that red dot and we are connecting it to I don't care about the phosphorus, because we just said those top 2 are confusing. Connecting it where on the blue structure? Where the oxygen is. So somehow or another, those 2 carbons are connecting to each other, and we can be fun with this. We're getting rid of that oxygen. So somehow or another, the carbon replaces the oxygen entirely. If this were to work, we should be able to identify charges to show that this would make sense. What charge would you expect for the red carbon? Why partially positive? Bromine is more electronegative, so it's going to withdraw those electrons. Fantastic. What charge would you expect for your blue carbon?
Also
Partially positive because? Oxygen is electronegative and withdrawing those electrons. Fantastic. So we're trying to form a bond between 2 positively charged atoms. Can we do that? No. We would need something. You mean like the first 2 steps? Yes. Okay. But minimally, by addressing those chemistries, we can at least get a feel for where they're coming from. Somehow or another, we're going to have to change those charges around to get the connectivity to happen. Kind of makes sense? Okay. Let's see. We've got a bunch more texts. Okay. So what we're guessing at, reaction or mechanism. What's the nucleophile? What's the electrophile? We tried that. And what did we end up with? We had 2 electrophiles. That's a problem. Okay. So at that point, we have to evaluate our earlier stuff to see what they're potentially doing. Okay? So look at your structures, identify their chemistries, see what can happen. We're going to end or go through a fancy little intermediate here that we haven't talked about yet, a yllid. Okay? Once we've identified those intermediate structures, we can go back to nucleophile, electrophile to see if that can help us predict our way through. Kind of, sort of? Okay. So, our first step, we've got our alkyl halide And we have PPH3, pH standing for phenols, so there are phenols. Okay? We know the phosphorus has a lone pair of electrons because we could go through and say it's in the same family as nitrogen. Nitrogen, when it's neutral, will have 3 bonds and a lone pair. Awesome, fantastic. Okay? The other option, you're damn good at Lewis structures and you can draw it out that fast. Should you be that good? Yes. Okay? It's partly what first semester was about, was just drawing Lewis structures so you get used to those patterns so you don't have to think about them. Okay? So we can now evaluate our 2 structures, nucleophile, electrophile. We have our carbon, which will be a positive charge. What does that mean we need to find in PPH3? We need to find a negative. We need to find a partial negative. Where do we find a partial negative? Why phosphorus? The lone pair of electrons on that phosphorus. Okay? On top of which, what else do we have out there? We've got these rings with all those pi bonds, which can potentially support phosphorus in sharing those electrons. For those of you screaming, doesn't that exceed the octet? Yes. Third row and lower can expand the octet if it needs to. So we are fully allowed to expand the octet. We don't have to, but we are fully allowed to do so. Okay? So we're now looking at that lone pair, okay, as our negative. Is there another positive in our structure, in our starting halide? Yes. Is there another positive in our starting halide?
Yeah.
Cool. Where is it?
The last carbon?
That last carbon? Okay, why would that carbon be positive?
Well, if the bromine is pulling electrons from that carbon's pulling electrons from the other carbon.
So an inductive effect, okay. If we reference and use that as an inductive effect, should you really be pointing at that green carbon as our other positive? We should be making what argument?
That would be the other one. But 2 positives wouldn't be together, so I just jumped in.
I like it. Okay, 2 positives wouldn't be together, so that's a possibility behind that. Okay, there is an inductive effect that could potentially deal with that, right? Okay, neither of those are our positive. What reaction did I just show? Red box. Elimination. What did I eliminate? Bromine and hydrogen. What charge was the hydrogen when it was removed so that I could make that pi bond? What charge was that hydrogen?
Negative.
Where did the electrons go? They went away from the hydrogen. That hydrogen is positive. That hydrogen is another site for reactivity. Okay? So now let's think about this. Okay? Because now what we're doing is playing around with this potentially as mechanism people. We know the end result. Is that positive hydrogen acidic enough to react? So we're asking, should this be an electrophile and a nucleophile, or should it be an acid and a base? If we did the elimination, where's the chemistry end up? Ends up in a double bond, yes. What carbons? 1 and 2. If we think back to our product, where was the chemistry? Should we go back to our last slide?
3 and 3.
We take a look back. There's our 1, 2, 3. There's our 1, 2, 3. Where's the chemistry in our product?
Okay.
It's at position what? 1. Is the elimination likely going to be taking us down a valid path? Probably not, and we would know that by looking at our product to evaluate this. That elimination is carrying chemistry away from where we know it needs to end up. Right? Those of you going, well, I wouldn't know that unless I ran the reaction. Exactly, that's why someone got to attach their name to this. Right? We didn't know that until we ran the reaction and saw what happened. Okay? So what does that mean happens over here? This carbon will act as an electrophile. This phosphorus will act as a nucleophile. If it's not going to act as an elimination reaction, it's going to run as a substitution. What mechanism do you want to show? Why SN2? It's a primary halide. Okay? We've run tests on the wittig reaction. Primary halides work better than all the others. What does that suggest? SN2 is a good call. We should be running this as a backside attack kickout. Okay? Does anybody have a problem with showing this as an SN2?
Well, your nucleophile is massive.
The nucleophile is huge. That would start to suggest that that's a bad idea. Does the evidence contribute to that theory? No. Okay? So what could we use to counter that being huge, now preventing it from acting as a nucleophile? Is there something else that we could say about that structure that actually it could act as a nucleophile and it isn't as big as we're making it out to be? Because when you're saying it's big, what are you saying is the problem? What's that? What sterics? The benzene rings. Because those are all very, very big. What can you tell me about phosphorus?
It's very big.
Phosphorus is also very, very, very big, which means those phenyl groups can get pushed relatively far away, and it can expose that lone pair on our phosphorus to be a little bit more active as a nucleophile. So we can make up an argument to show that steric effect being minimized by the size of that phosphorus.
Ultimately, it doesn't really matter because we see it do that. And
There's a mix on that. So we couldn't go, oh, it doesn't matter because it happens anyway. We need to know why it happens so that we can apply that knowledge to other cases. Because if we don't know why it happens, we have to memorize every single one of these things as an independent fact. We want to have rules that we could apply out to other situations. Right? And because of those d orbitals, phosphorus and sulfur do really weird chemistries. Right? Which is also why, as organic chemists, you typically see people avoid those reactions. And we don't talk about them as much because their chemistry is a lot more complicated. Right? So the end result is we get a substitution. Right? The phosphorus, by donating those electrons, becomes positive. Right? Is phosphorus happy as a positive? No. Charge is inherently bad, so that's not a good thing. So let's fix it by moving on to step 2. Right? Oh, sorry, before we do that, we did address these. Just want to make sure you remember them. Primary halides work best. Okay? And really what we're doing is priming the carbon to hold a negative charge. Okay? Which isn't obvious yet. We follow this up with butyl lithium. We wrote it out as butyl lithium intentionally to hide the structural information. Now, since I want to talk about the structure and how it could react, we've got the structures written out. Notice 2 possible reactions. Okay. What do we see as the chemistry of butyl lithium?
a nucleophilic carbon.
Okay. Nucleophilic carbon, take a step away from all those science terms.
Carbon and lithium.
There's a carbon-lithium bond. What kind of bond is that?
Ionic.
An ionic bond, which means they split into the ions. That would better be represented where the electrons in that bond go where?
On the carbon.
Specifically to the carbon, negative, lithium, positive. we now have a negative carbon. So it could act as a nucleophile or a base. Funny how there's two little things there, right? You're like, that's super hilarious, Mike. You should be a stand-up comedian. Okay. What would happen if it acted as a base? What would happen if it acted as a nucleophile?
If it acted as a base, it would pull off one of the hydrogens next to the hydrogens on the propyl chain next to the phosphorus.
So, red, blue, green. Which one is the worst idea?
Green.
Why?
Because there's nothing to stabilize it. It's leads to a primary.
We'd have a primary anion, and there's nothing to stabilize that negative charge. Okay? We then have two options, red and blue. What if we did blue? We'd have a negative charge, right? Could I stabilize that negative charge? Does phosphorus want to be positive? No. So what might it do? What might phosphorus do to stop being positive?
Grab that pair of electrons and make a bond.
Grab those electrons to make a bond.
Sorry, the lone pair. Grab the lone pair of electrons and make a bond.
Okay, how stable are electrons? Not stable at all. Are the electrons going to be able to travel through space to get to that phosphorus? No. Phosphorus is not touching those electrons. At best, it will touch the electrons in the bond immediately next to it. Would that stabilize that negative?
It would in the second one too. There we go.
Wouldn't that work? That sounds an awful lot like backtracking. Why didn't you just add a base outright with the alkyl halide to begin with? Wouldn't that have gotten me a pi bond?
Yes.
Yeah. So maybe the phosphorus is doing something else weird. Maybe it's not that hydrogen that is acidic. What if we removed the red hydrogen? We'd have a lone pair on that carbon. Can carbon stabilize that?
Phosphorus can.
Carbon cannot stabilize that negative charge, right? That's what I'm hearing. That is impossible. There's no way it could stabilize it. Nothing that, like a little bit of resonance couldn't do to, stabilize it.
Is that the carbon or is it the phosphorus stabilizing it?
Okay. That negative carbon can absolutely be stabilized through resonance with an overlap with the pi system of the phosphorus. Expanding octets. That's not allowed to happen, except it's a third row element, d orbitals, F life. Yep, can do it. Okay, absolutely fair game. Okay. What else could it have done? If it, instead of acting as a base, it acted as a nucleophile. What would have happened then?
Phosphorus.
That negative would attack where? Could attack the phosphorus, and we'd form a negative carbon. Is that negative carbon any more or less stable than what we started with? No, so I don't like that idea. Maybe we shouldn't attack the phosphorus. Maybe we should attack that carbon, ejecting phosphorus. Phosphorus, pH, pH, pH. We already heard a comment about this. Isn't that taking us backwards? Yes, it is. So probably not a good idea. Let's add to that what happened to our structure. So there's our starting 3 carbons. There's our new bond. And now here's our 1, 2, 3, 4 carbons. What did we do to the reactivity of our target carbon?
Eliminated it.
We completely killed the reactivity there. All of these things are possible options to consider. Only one of them takes us forward towards the mechanism or our end result. Okay? What I want you to be able to recognize is all of those possibilities. I want you to be able to recognize that if we did that chemistry down below, where do we go? Nowhere. Not useful. You need to be able to draw out arrows and mechanisms and be like, that did not work, so that you can double back and try a different route, a different path. It is that iterative process that is going to be useful for reactions that you've never seen before. The flip of it is just memorize all the reactions, and I'll see you in 10 more weeks. Okay. Yes.
Why can't the negative carbon attack the positive phosphorus?
What do we end up generating? An equally negative carbon. There's no driving force for that. We aren't forming anything more stable.
Why would that make a negative carbon?
What happens if that negative attacks the phosphorus? Whoops.
I mean, why can't it get another bond on there?
Attack the phosphorus. It's already positive. Okay? We're already maxing out octets. The exceeding of an octet is not that I've added more electrons into the structure, it's that I already had those electrons to stabilize.
Okay, so it still can't break octet. It can't shove those into the d orbital? That's what I was wondering. Why can't you like pump them up in the d orbital and make that?
To what end?
Just an extra bond? Because it's phosphorus and N. Why can't
Okay.
you do that?
Did that do anything to affect the chemistry of that other carbon then?
Yeah, it'll kill it partially because
It makes it as equally active as this to begin with. In which case, why did you start with the alkyl halide? So if you try and run that reaction without it eliminating and just leaving it on there, what have you done that was productive? Okay. At best, you now have 2 reactive carbons. That means more products. We didn't get more products, we had 1. And it was the 3 carbon, not this 4 carbon of the butyl lithium. If I could have just directly attacked it, then why didn't I do that to begin with? Why did I start with an alkyl halide? All of those reagents are there for a reason. If you can't explain the presence for that reagent, then the mechanistic step you're trying to do probably wasn't useful.
Okay.
Right? The fun thing that we get here is what is now known as a yllid. We have a negative next to a positive, okay, through kind of a phosphorus or a sulfur. It's usually a 3rd row element. Okay, that's known as a yllid. You can do it with sulfur or phosphorus. Those are the big common ones. Okay. Phosphorus just happen to be the one that we've worked with most commonly in OChem. It can happen with sulfur, typically in some form as a biochemistry reaction. Okay. That's now a yllid. Why is that special? What did we just make our carbon? Negative. What did we need it to be? Negative. So what can we do? We can now actually push that to the next stage and form a bond with our carbonyl. Okay, for those of you that enjoy mechanisms, this is a real fun one. Okay, before we get there, I do want to double back here. We do have that potential for a resonance stabilization, negative to positive, forming that pi bond where we're exceeding that octet. That doesn't happen very often. If you're asked to draw the best Lewis structure, interestingly enough, it's the charged one, not the other one. Why?
too high electron density around the phosphorus.
Nope. if we're making that pi bond, the carbon is effectively sp2. The phosphorus has to have a mirroring p orbital to overlap, right? What p orbital is the carbon going to use? Carbon. What p orbital would the carbon use to make a pi bond? It has to be a p orbital. It's a pi bond.
So one p orbital that has left.
What p orbital? I don't know a p orbital.
One coming
Doing
through.
that gesture is pretty good, yeah?
Two.
2. The 2p orbital. That's what it has. What is the phosphorus using? 3. So if we look at this, here's our carbon, p orbital. Here's our phosphorus, p orbital. What's the overlap? Relatively minimal. We get a huge section of the phosphorus p orbital that doesn't overlap with the carbon. Because there isn't overlap, there's no pi bond. Okay? We have the ability to pseudo fake it and say there's something there to kind of stabilize it. And we can fake our way through calling it resonance, but for the most part, it's not there. Okay? And that's a tricky concept to deal with. But I want you to at least be aware of it. Okay? So now what happens? Okay? One thing that can make you kind of happy on this is notice it says mechanism, debate. If there's a debate, what does that mean?
We get to fight about it. And we're not responsible for it.
We're not responsible for it. Okay? We do need to understand some basics of it. So let's look at some patterns behind this. How would you predict this reaction to go? What's the most reactive thing you see?
Negative carbon.
Negative carbon. Where should that negative carbon react?
With something that's
Partially positive. For those of you who are like, I don't see a positive. Okay, that's okay. You should see a pi bond. And the instant you see a pi bond, you should be like
Isn't a polar bond.
resonance. And when I draw that resonance, what do I find? A positive. Where should my negative carbon react? With the positive carbon. Okay. Now the next fun part. If we did that, what do we get? I'm going to attempt to draw this nicely. And I'm just going to draw this as PPH3. Put the positive there. We'll see why in a second. Here's our formed bond. There's that O minus. Methyl. Yeah? Everybody see it? Ish? Everybody see it ish?
Could be seeing issues.
No. As in sort of, kind of.
Yeah.
Yeah. Is that structure stable?
No.
Why not?
It's got a positive and
We have a positive and negative. In particular, where is the positive and negative? Right next to each other. What might happen? This is the mechanism debate, deciding how we get to that structure. Okay? Based off of where all the orbitals are, we could make an argument that it forms simultaneously across that. Okay? We don't really know. Okay? But we end up going through and forming this cyclic intermediate. So we know this exists. Was that our final product?
No.
What did we need?
A pi bond.
We needed a pi bond. A pi bond between what two atoms?
Carbon and carbon.
Our carbon and carbon. So we needed a pi bond running through there. To make that pi bond, what do I need?
Electrons.
Electrons. So I need to find electrons from somewhere. Okay, what do you think? Bonds. Which bonds? Should I break this bond? Should I take that one? No, why not? So if I take the electrons from the sigma bond to make the pi bond, do I have two bonds anymore? No. I would now just have a pi bond, which doesn't make any sense. It would have just changed to a sigma to a sigma. So that one doesn't work. How about this one?
No.
Why not?
Takes us backwards.
It's too far away. Remember, where am I trying to get? I want electrons in here. That red dot has those electrons way too far away. So I need to be getting electrons from one of those side positions. Should I take them from the oxygen or the phosphorus? Why?
Oxygen is electronegative.
Oxygen is more electronegative than phosphorus. Cool. So we'll take the electrons in that side and we'll go, boom, pi bond. Immediately, what becomes a problem?
Your octet.
We've now exceeded the octet.
So the oxygen leaves.
So now the oxygen says, well, Fu carbon, I'm taking my electrons with me. Boom. Shares them with the phosphorus. The phosphorus just lost electrons. That oxygen can now share those electrons with that phosphorus that it just lost. What we're getting is a cyclic elimination reaction. We form our pi bond, and we end up with this relatively strong phosphorus-oxygen bond. Oxygen is smaller than the carbon. The oxygen-phosphorus bond is a shorter bond than the carbon-phosphorus bond. We now have our elimination product. Kind of neat. Questions? Okay, my turn. Anybody see a potential issue popping up with that product?
Yes.
Yeah? What's that issue?
It's got a pi bond.
It's trans.
What do you mean it's trans?
Well, I'm assuming it's trans. It looks like I don't know if I actually can call it.
That structure is a trans pi bond.
Yeah. We had a cis pi bond.
Couldn't have also organized in a fashion to get the cis pi bond? You're shaking your head violently no. Why? So p orbitals, the pi bonds can't rotate once they're formed. That formation all tied back to this structure. That structure that was actively under depending on the substituents of your carbon structure, it will change the preference from cis to trans. How many people want to memorize that relationship? Good, don't. For the Wittig reaction, we know we just make the pi bond. Okay, that we connect those two through a pi bond. That's it. You don't have to worry about cis-trans specificity. Okay. So you should not be seeing an answer choice that has one answer cis and one answer trans. Okay? Unless there's also an answer choice that says both of the above. Does that make sense? Okay. It is a very active area of debate. Depending on the substituents, you get different results. Okay, it does change. Okay. So ultimately what happens is you convert your carbonyl to an alkene, and at the same time, you make a larger structure. That's kind of cool. We don't lose any functional group or functional group reactivity, because we still have now two active carbons because the pi bond is now between two carbons, so that's cool. And now we have more carbons to react. That's neat. We do get this mixture of E and Z isomers, and that can make it a bit more problematic to deal with. But hell, we've made a larger structure. We can deal with that later. Okay, so that's the Wittig reaction. I don't remember what the next one is. So before we do that, the next slide, I'm going to double all the way back. Hopefully I won't regret too much. Got to do it kind of slowly. Do we have a cheat? Yes. Yes, we do. I want to be able to draw the product. How many of you think you could draw that product really easily right now? Okay, let's fix that. We need to remember that our alkyl halide is going to become the nucleophile. So here we go. I'm going to draw that nucleophile. Notice that this carbon is kind of aimed upwards. I want to make that connection to the electrophile. So I'm going to flip the structure. So I'm going to go this way. There's the bromine. There's my nucleophile. I know the bromine is going to disappear, so what am I going to do? I'm going to erase it. Okay. I'm now going to go take a look at the electrophile structure, and I'm going to place that electrophilic carbon right there. Okay. I'll even show the oxygen going upwards. Now I'll drop in the rest of that structure. What happens to the oxygen?
Goes away.
Disappears. What happens to the pi bond?
Stays.
Connects it. Overlay the structures on top of each other, erase your oxygen, complete out the double bond, you're done. Okay? With a pseudo exception. The odds that it shows up like that on an exam are next to nothing. Okay? How is it going to show up on the exam?
The way you had it shown originally?
You're like, dude, what the hell? What happened?
You moved it.
We showed the longest carbon chain running in the zigzag formation left to right. Okay. It is still possible that they could show cis versus trans. Like I said, cis versus trans is not hashed out yet. So more than likely it would always get shown in the trans configuration as opposed to the cis, because in that trans configuration, it's going to prevent that cheat method from being directly copied across. You can't just draw that and get directly to the answer. Does that make sense? You'd have to do a little bit extra manipulation in your head to jump. Kind of good? Okay. So with kind of good, what does that mean we should do? Yeah, we should practice. Why not? So, 3 questions. All of these are wittig. Okay? You might notice they all don't have the same format, so be careful with them. See what you can come up with. So, I did see people going through showing a mechanism. While I like that, okay, that is a good thing to go through and get used to. This has multiple steps, multiple mechanistic pieces, lots of things flying in and out. It probably makes sense to just kind of cheat. So if we flip it upside down, whoops, except you got to make sure you have the right number of carbons. Is it 4 carbons? 1, 2, 3, 4, 1, 2, 3, 4. That's where our bromine would be. So I'm going to erase that, put the dot so I know that's where my chemistry is. Okay. You'll notice that I'm now searching for the carbonyl, is the other half of this. So there's the carbon, there's my carbonyl. Okay. And now recognizing that to the sides is a CH3 and a CH3. Okay. So what happens? I erase the oxygen, complete with the double bond, there's my answer. Relatively quickly. Okay. What makes this one more challenging is that carbonyl structure was shown in the line format, which is really irritating and frustrating. You're responsible for knowing that. So that's why you're seeing the question show up. Give you a little bit of practice with it. With the next one, wittig is 3 reactions. Why is this only being shown as 1?
Is it just the helix? Is that your helix?
Okay. I got rid of the first 2 reactions. That middle structure is our intermediate. It's the ylid. Phosphorus pH3, there's our positive, carbon negative, CH2, CH3. Okay, officially I left off that hydrogen. There's our nucleophilic carbon. That nucleophilic carbon comes in and attacks, busts, does it a couple times. Let's see if I can actually do this in that orientation. So we've got our pi bond. Let's do that in black. There's our pi bond. There's our red dot carbon. 1, 2, 3, 3 carbons, and the ring. This is one that it's going to be really easy to lose carbons on. Okay, so make sure that when you make that connection, you don't accidentally delete a carbon. Does that make sense? Okay. Last one, 2 methods. Okay, you're being told it's wittig, so that helps. That means we're cleaving around that pi bond. So we could either do the structure. Say that again. Not again, but what's your question?
I think you gained it.
Yeah, you added a carbon.
Yeah.
Oh, I did. You could also add carbons. Make sure you count them. 1, 2. Damn it.
Yeah.
1, 2, 3. There we go. Okay. It's very easy with the carbon adding structures and removing to lose track of those carbons. It can be helpful to count them out. As a hint, 6, 7. So I've got 7 carbons plus 3. So I've got 10. There's 6. 1, 2, 3, 4. There's 10 carbons. Okay. The 2 wittig methods, so we can cleave, we could go through, do the carbonyl, and then the other half be the bromide. Or we could cleave, do the bromide, and the carbonyl. Kind of makes sense? We don't care about all the other reagents because those are what's going to get these 2 things to react with each other. Okay? I already heard someone start to ask. I asked for 2 wittig methods. Now I'm asking for 1. By asking for 1 wittig method, what does your answer become? Why is the answer now only the blue one and not the red one?
Does the red one have the acidic hydrogen?
Do you have a primary halogen?
The very first step of the wittig is that you react the phosphonium compound with the alkyl halide. That was an SN2 reaction that works faster with primary halides. The purple one's the better one than the red one. Do both work? Yes. Will both get you the product? Yes. But if you're forced to choose between one or the other, you've got to recognize the process of the mechanism. Make sense? Okay. Yeah, go for it. More practice. If we do the wittig, we're now adding 1, 2, 3 carbons. 3 carbons will make it a halide. 1 triphenylphosphine. Whoops, too many chimney. pH 3. Butyl lithium. And then 3 are cyclohexanone. Everybody get that? Did I do that right? Okay. What's the second method? Okay, that's harder because I'm pushing you on a synthesis here. Okay, what is the difference between the starting material and our product?
Lost oxygen.
Lost an oxygen, yes. What else?
Gained 3 carbons.
I gained 3 carbons. It's a really important aspect. I had to somehow connect 3 carbons to that starting material. What charge did my carbon start as? Where's that carbon in my product? Right there, right? That's a partial positive, which means this carbon, when it makes that connection, somehow through this reaction has to have what charge? How do I get a negative carbon without doing a wittig? Give it a shot, see what happens. For those of you that may not have heard that, MGBR, I believe was the hint. It's a good hint. It also doesn't solve the reaction I just showed, that red arrow. Very difficult to predict where you need to go if you don't have the product shown, kind of for the record. Tax. O minus. 1, 2, 3. What needs to happen?
Get rid of the oxygen.
I have to lose the oxygen. What else?
Form a double bond.
Form a pi bond. How do I form a pi bond? What kind of reaction would that be? An elimination. To do an elimination, what do I need?
Water.
What do you mean?
I really don't know why I said that.
Borderline could work.
I need a base.
Okay, we could argue you need a base. Why do you need a base?
To pull off
Because
the
I'm gonna have to get rid of a hydrogen.
Okay. One of the results is we're going to have to remove a hydrogen. What else has to happen when we do an elimination?
you know, leaving group.
You need a leaving group. Is oxygen a good leaving group?
No.
So what would you need to add? Hydrogen to it to make it into a leaving group, which would mean you're running under acidic conditions, so the base is going to be problematic. Okay. But what happens if you just add an acid and a bunch of heat?
Break the bond.
You would get an elimination. So we could do H2SO4 and heat. What would happen? That's a 2. We'd have a good leaving group. I don't think that 2 looked any better. We'd have a good leaving group, and now we'd want to do our elimination. Where would we eliminate? Where is there a beta hydrogen? 1, 2, 3. Well, 3 different beta hydrogens, which means we could get 3 different products. That would not be the greatest synthesis, but would it get us there?
Yeah.
Yeah. Right. So the Grignard mechanism could work. Are there other ways that you could help try and push that? Instead of going to water as your leaving group, we could make it
OTS.
OTS. Okay, we could react it with tosyl chloride to make it a very large leaving group. Try and use a more hindered base. Maybe that purple hydrogen is slightly more accessible than the red and green, not by much, right? And we might be able to get the elimination happening outwards. In all 3 cases, they're all tri-substituted pi bonds. You're not going to get very good results, which would be a reason why, given this reaction or this question, we were told to provide a synthesis. Which one should you choose? You would need to choose the wittig. The Grignard would work. It doesn't work as well. I will say that when I grade syntheses, as long as it works, even if it doesn't, well, as long as it works to some reasonable extent, I usually accept it. It's when it doesn't work or it works horribly that I don't accept it. So if I asked this on an exam, provide a synthesis, and you gave me the Grignard one, that Grignard path, I would accept that. And I would give you points for it. But I would also write, there's a better method.
You said use a bulkier base. I thought you said we were not using a base. Is that not?
Once we converted it into the tosylate, now we can use a bulky base. Because now we aren't having water as a leaving group, we have the tosylate as a leaving group. I can switch to a base. So the only reason I can use a base is I'm not using water as a leaving
That
group.
was assuming you're using tosyl chloride. I just
Yep.
wanted to be clear.
Nope. That's why you would use it. Okay. The textbook used to have some information on sulfonium ylids. It looks like it's been removed from the textbook. Okay. So if you're using the second edition, it's not there as far as I can tell. There is a question on it in the smart work because I wanted you to see it. Because sulfur's chemistry is similar, and I think there's many reactions in biochemistry that mirror this kind of Ylid reaction through sulfur. Okay? So I wanted it to show up so you get a little bit of background with that. We can take DMS, react it with methyl iodide, and then a strong base. That gets us our sulfonium Ylid as opposed to a phosphorus Ylid. Okay? Now that negative carbon can react with, whoops, it's not on here, can react with carbonyls, and we do a slightly different reaction. We end with epoxides. Okay? Why do we end with epoxides? Because of the charges of the individual pieces, and the chemistry changes around a little bit. Okay? So don't stress a whole lot about it. I will say it is in Smart Work. These slides are the things that you would find in the textbook. Okay? Because it's not in the textbook, what I'm strongly considering doing is going through and just removing the point value to 0 for that particular question, because it only shows up once. Yes?
The DMS is just a
Source for the sulfur that doesn't introduce potential nucleophiles, secondary nucleophiles.
there's a word that it replenishes itself. It's just a catalyst, essentially. Or is it like because of so many different steps, it's no longer?
I think officially it does go through as a catalyst because it's not consumed nor is it destroyed.
Okay.
So I think it does officially classify as a catalyst. Which is kind of weird because you are using it. This is a reaction out of biochem. Really kind of complex. Don't stress about it. It's not actually in the slideshow. That sulfur carbon nitrogen structure is generating a negative carbon. What did we generate in the phosphonium yelid and the sulfonium yelid?
Negative carbon.
Negative carbons. Okay, so it's the proximity next to the rest of that structure that actually makes that carbon nucleophilic. This is running the reaction of converting. Anybody take biochemistry? A couple people have. Let's test you.
Okay.
Starting material, product. What did we do? This is why I don't like biochemistry. All they use are freaking names. They don't talk about the structures. It's pyruvate and acetyl-CoA. This is the mechanism to shift from pyruvate to acetyl-CoA. Okay, so it's a step of glycolysis. Okay, we're officially past time. We will give you the first 5 minutes of class on Monday looking at this reaction. I think we're doing okay as far as slides go. Yeah, we're doing pretty okay. So I'll give you 5 minutes with this reaction on Monday. Yeah, I think we'll say that. Okay. So I would recommend you try and take a swing at it anyway. Might show up on exams, kind of, as potential questions.